two of us. I don't want to be the only one.
Well, we'll go ahead and get started. If Pete comes in, Pete had offered to make a few statements to introduce this subject, and we'll stop and hand it over to Pete at that point. Let me say, first of all, what a joy it is to be able to share this topic with you. My thanks to Yvonne and Greg and Pete, not only for hosting this, but giving us the invitation to come and share some exciting data and information with you today. You know, it's in thinking about this, it's during this time of the year, the anniversary of Apollo 11, that we look at the moon, and I saw it earlier today. It's still out there, we're visible even in the daylight, and ponder that time in history, man's first exploration on the moon. And you know, from that, in my thinking, it doesn't take much for the mind to wander some interesting questions about the hardware and artifacts that we had left there, like what has happened to all the hardware that we had left at the Apollo sites? Do they look differently there today than we first placed them there in the late 60s and early 70s? Is the flag still standing? Is the flag even still there in the intense UV radiation there at the moon? Is the hardware still in a pristine state as we last left it and saw it? Or has it been ravaged over these many years by the harsh lunar environment? Is the RTG still powering any of the equipment out there on the moon? Is it still active? So is anything left that's even non-metallic at these Apollo sites? We don't know, but I would tell you from my perspective that we're about to find out the answer to these questions and many more, and not in 20 years, and not in 15 years, but as early as just over 2 years from now. And you know, today is an important day for us because it marks the first public disclosure from NASA in dealing with this subject that we've been working on for some time, on dealing with the Apollo sites and the near-term visits of these visiting vehicles to these sites, but also taking it from a perspective of the scientific and engineering value that these sites offer upon returning to them. So it's a very compelling story, it's a very captivating story, and in many ways it's very exciting to the imagination and the heart as we tie back into the Apollo era as well as we look forward. Now I have to tell you, as a former shuttle flight director in mission control in the 80s and 90s, I had to get up this morning and watch the final flight of Atlantis and STS-135 and the end of the shuttle era. It was tough to get up at 2:30 in the morning, and ABC didn't really show it until, or Fox didn't until just a few minutes prior to landing. But I thought, as I was watching that, how ironic. Because in early 1972, President Nixon announced the end of the Apollo era, America's manned flights to the surface of the moon, and yet the start of the shuttle program. And here we are on July 22nd, 2011, the end of the flight program for shuttle, and yet we are at an opportunity, an entrance to restarting surface exploration on the moon. It's quite the antithesis. So today, what we're going to share with you within this NASA panel discussion centers on a couple of things: risk versus risk and risk versus gain associated with small spacecraft visits to the U.S. government lunar historic sites. And with those sites and with those visits, we run the risk of inducing irreparable damage to over 40 years of sitting on the lunar surface. And yet, similarly, we have a great opportunity to gain in very interesting knowledge scientifically and from an engineering standpoint within NASA of knowledge associated with the hardware at these sites and understanding the effects of long-duration exposure in the lunar environment on optics and thermal control systems and materials of the artifacts that have been left on the surface, with them in true sense representing continual experiments or witness plates to the lunar environment over that time. So the question that we have been dealing with over the last 9 months within the agency deals with how do we safely access these sites such that we can assess these sites from an engineering and scientific perspective without inducing damage and contamination to the very sites that we want to visit. So there's a number of things that we're going to share with you today. One is to set the stage with some fundamental analysis that's been gone on, in some cases, 10 years or more out of the Kennedy Space Center, more recently in the last 8 to 9 months within the agency. We want to share some of the challenges that we have identified through these analyses as we look at returning to the Apollo sites. We want to share with you the top-level recommendations, a subset that's in the full package that I have up here if you would like a copy. So some of the top recommendations that came out of our NASA group. And then the two appendices out of this report deal with a lunar science perspective and an engineering perspective of the value that returning to these sites offer. You know, it's startling to me that the last time we had a U.S. lunar surface asset there at the moon was Surveyor 7 in January 1968, 10 months before we launched Isley and Cunningham on Apollo 7, the first flight of Apollo. And of course, the last time we were on the surface of the moon with the human presence dealt with Apollo 17 in December of 1972. And yet for the last few years, we have seen tremendous data out of the orbital assets from the US, China, Japan, India, that has revolutionarily changed the way that we see the moon in ways that are radically different than the way we viewed the waterless moon of many years ago during the Apollo era. And so, in my perspective, it is time to re-engage the surface of the moon that we have not done so in 40 years. You know, almost my entire career, we have not been back on the surface of the moon. And yet we can do this to begin to get lunar surface analog data, flight test data, to collaborate against the orbital asset data to establish ground truth in these endeavors. And in truth, there's a number of, to their credit, a number of groups that are planning to go, include China, India, Japan, ESA, are all advertising in preparation for flights in mid-decade to the moon, to the surface of the moon. And then we have on the private sector, the commercial sector, the Google Lunar X Prize, the $30 million prize through the Google to the X Prize Foundation with 28 teams across the world dealing with going to these sites. And as a part of that prize is a $5 million augmented or heritage prize for a group that first goes to a lunar historic site. When we look at the moon, this is a graphic showing all the impact sites and the landing sites, both internationally within the United States. But within the Google Lunar X Prize themselves, there are teams that are looking to go, at least 2 teams going to Apollo 11, a couple of teams interested in going to Apollo 12 in the Ocean of Storms, at least 1 team interested in going to Tycho Crater and looking at Surveyor 7. And so they have become to the point to ask NASA early on for help in trajectory and guidance and risk assessment associated with the visits to these sites. And as we look at these lander systems, some of them rove, some of them hop across the surface, some like Surveyor, some like Mars Exploration Rover, and yet it allows us to take advantage of some of these assets in the next couple of years in a couple of interesting areas. One area is in the historic value associated with these heritage sites, and then also the scientific value from engineering and lunar science that these visits apply. And what are some of the things that we're interested in seeing at these sites? The descent stage that's been sitting there, the tanks, the MLI blankets, the structural members associated with the landing gear, the Apollo Lunar Surface Experiment package that had an array of different styles of thermal control systems, of power systems, of materials associated with that. How have they survived over 40 years? Of course, there's the flag. You know, is the flag still there? Some people think within the community that the flag essentially vaporized in 1980 that it was gone by that point? We just don't know until we get to the site. There's the, I think it went one too far. Let's see, did I click it wrong? There's the footprint. Let me see if I missed one. Nope, yeah, it did. I missed two. It's bouncing across. One is the Lunar Roving Vehicle, which is a vehicle integrated system of itself, combined materials, nylon straps, that is of great interest within the agency. There's comm antennas. Has the wire mesh survived? Has the strut survived on high gain, low gain systems from an engineering standpoint? Of course, there's the footprint in and of itself. And then there's areas of interest. So this is the Dave Scott at Galileo Experiment, where he dropped the hammer and the Falcon Feather from the Air Force Academy. Of course, the lander on 15 was called the Falcon, showing that things drop in the vacuum at the same rate. And so there are people within the biological community interested in seeing the feather and see how well biological systems have survived over 40 years on the lunar surface, if at all. So there's a number of areas that are of interest out of this and returning to the sites from a science perspective. Biology, planetary science, space weathering, but more specifically, questions that dealing with dust transport. There's a big debate over the levitation of dust, the electrostatically levitated dust. And so perhaps we can get some ground surface flight data to help corroborate whether that levitated dust exists or not. Micrometeorite bombardment. We have the radiators sitting on top of the battery packs of the lunar rovers that are at the 15, 16, 17 site that could very interestingly give us some idea of the 40-year micrometeorite flux during that time period by re-examining the glassy surface of the radiators on top of the LRV. Sandblasting effects. So the effects that we didn't get to look at in Apollo from the subsequent ascent by looking at the sides of the instrumentation and hardware facing the ascent versus the sides facing away. And then there's the areas that Mike Squire from Langley is going to talk to you about, dealing with space weathering across a wide range of materials and over 500 lunar cycles from plus 250 degree F to minus 300 degree F, how that has affected the hardware over years. And then the Astrobiology Institute is very interested in the biological and microbial aspect. We had at the Apollo sites, of course, the ascent stage, if Jeff finds that for us, it is filthy with human activity and microbes and biological activity. The crews took defecation bags and urine bags and food bags and put them in cloth bags and jettisoned out the limb or put them under the descent stage on their last DVA that are sitting there. So how has gene expression and gene mutation and these microbes survived, if at all, over 40 years of sitting on the lunar surface? And so there's a number of risks, however, that are imposed by going back there that will qualify for you. One is the very act of going there and erasing the footprints or dusting the site artificially that could interfere with the data that we want to get relative to dust. Same thing with not only landing, but in the roving, the casting or throwing of dust through the wheels. Biological contamination, of inadvertently contaminating the site, and then during descent and landing errors that could represent dust clouds inadvertently kicked up on the site or even the collision potential. So today what we want to do is give you a feel of some of the background data. Dr. Phil Metzger from Kennedy Space Center has been spending 10 years looking at high velocity particle interaction of ejecta from descent engines as associated with the lunar regolith. Jeff's going to come up and show you some of the imagery we've been using associated with the heritage sites. You saw some of that this week. I'm going to give you an abbreviated version of some of the high-level recommendations that's in the package that we're announcing today. And then Mike Squires from Langley is part of the NASA engineering safety team, and he has engaged PhD experts in optics and contamination and processes, materials across the agency, in looking at what we can learn by going back and looking at the hardware within the Apollo sites. And then Dr. Cohen, Wendell, others within NASA have been looking at what scientific value we can get by going back as well and looking at the Apollo sites. As we put the next charts up for Phil, I'm going to ask Dr. Warden come on up and say a few words as he introduces this subject as well. Pete?
Sorry, I'm a few minutes late. It's the usual. It's the story of my life. But this is an incredibly important topic. I remember a few years ago when the Google Lunar X Prize started, some of the folks came over and said they're really looking forward to this, and that the prize might be to go up and take a picture of the first footprint for Apollo 11. And so I said, well, it's really neat. And then I got to think about it. And I said, well, what if they knock over the flag if it's still there? And what if they screw up and they roll over the first footprint rather than take a picture of it? So I think about 4 or 5 years ago, I asked a few people to start looking at that, and Rob got very interested in it. And it's pretty clear that we are on the verge of a lot of people going back to the moon, and not the least of which there's a lot of legal issues. The hardware still belongs to the country that launched it, but what about the place it sits? And it obviously has huge cultural and historic value as well as incredible scientific value, as Rob discussed. So this is a very serious topic, and the interesting thing about it, I think, is that as we are on the verge, in my opinion, of the permanent human expansion into the solar system, there are incredibly significant cultural, scientific, and heritage and policy questions that we will begin to solve for all time. So how we do our work and how we curate things and how we gain the maximum knowledge will depend on the next few years and the work we've done to date. So I can't imagine a more fitting and appropriate topic than understanding, okay, what is it that we can gain from revisiting human visited sites? How do we preserve them for posterity? And what does it mean for our future? And what does it mean for who and what we are? As we speak here, just across the campus here, there's an organization called Singularity University that's looking at what the future of, humanity is, and some of them think that we're all going to download ourselves into computers. That may make some of these cultural sites even more significant as the last remaining, remnants of humans. So I think that this is really a topic of incredible import, and it's also one that the public has a huge interest in, and of course it's the public that's going to finance our expansion into space. It's the public that frankly finances the private sector that we're counting on to move these things forward. So as you come to understandings and conclusions, I would urge folks to consider, how do we communicate what we learn and what we think about this stuff to the public in a way that is positive. I mean, I've had a lot of bad experiences with negative communications to the public. In fact, some of you may know that I got in a little trouble for some comments I made about L-Cross bombing the moon. Some of you have heard this story, but I'll have to repeat it. So I do put this as a cautionary note. I'm a retired Air Force Brigadier General, and I was really excited with L-Cross because it's the first time I got to sit at the adult table at KSC for the launch. For those of you who've been down there for a launch, there's a room the size of this or bigger, and there's a wooden table in the center where the principals sit. They do their final launch readiness poll, and they went around the table to launch services go, range go, so on and so forth, and Goddard Space Flight Center for LRO go. Then they got to Ames Research Center, and I said, Ames is go for the first precision bombing run on the moon. And that would have been all right. Everybody kind of laughed, but I thought it was cute enough. I put it on Twitter. And so you got to be careful what you talk about these things. And it turned out somebody in Seattle put 2 and 2 together, get 86, and said, Air Force General bombing the moon. They remembered that some of the Apollo astronauts had communications with aliens, and that Clementine allegedly had found some alien base on the moon. And they had it all what we were doing. This was a CIA plot to start a to bomb these alien bases and start an interstellar war. And so somebody also found my email address. So I must have got 200 or 300 emails from, I'm a mother, I have a 3-year-old and a 5-year-old, I want them to grow up, please don't start an interstellar war, my kids deserve a chance. It wasn't too long after that a certain congressman from Ohio got a hold of General Bolden, and he was just hopping mad. He said he was going to do a full hearing about what's the connection between NASA and the CIA and this. And so I won't mention his name, but you can probably figure out which one. And so I got a counseling session with the boss, which was not positive. But I haven't used Twitter really much since then. I think it's a bad idea. So it is important when we talk about these things that have incredible public and cultural interest that we think them through. And even though it sounds like kind of a cool thing to do at the time, be careful what you say. So that's one of the cautionary notes. But at any rate, I think this is a great topic, and I look forward to hearing what you have to say. So Rob, thanks for organizing, and the rest of you, thanks for being here. By the way, we did have a precision bombing run. We got within 100 meters of where we were. So that's pretty good.
Okay, so I'm Phil Metzger, and as Rob said, we've been working on studying the blast ejecta problem from rocket exhaust interacting with soil for about a decade. I was asked to do this originally for the ISRU program, because if you're going to create propellants and a fuel depot on the surface of the moon or Mars, then by definition you're going to have to land near it and launch near it. And when they asked me to look into how to build a landing pad. And when I first started working on it, I realized right away that there was a lot of physics that we didn't understand about the rocket exhaust blast effects. And before we could define requirements for a pad, we really had to understand the physics. So I went off and spent the next 10 years working on this problem on just understanding the physics of it. And it's been a collaboration of a lot of people over 10 years, and I think I'm even missing a few names here. I'm not going to read the co-authors, but so with a little bit of time that we've got, I'm going to go through an overview of the phenomenology of the lunar case, which is a lot different than the Martian case and a lot different than a small body case. I want to talk about why it's important, what kind of damage can occur from a rocket exhaust in the lunar case. Where does the ejecta go and how fast does it go? At what height of the lander will the blowing begin? And how much material is blown, which is the most difficult question to answer. And then I'll briefly mention multiple engines and shock effects. So first of all, overview of the phenomenology. The rocket exhaust case for the moon is completely different than the Earth or Mars. These are simulations that were done with the appropriate atmospheres for each of the three cases. And for Earth or Mars, there's an atmosphere which collimates the rocket exhaust plume into a jet. In the lunar case, there's no jet because it's expanding into a vacuum, but you do get a broad shock wave that forms over the surface of the moon, and there's a stagnation region. Most of the mass does come down the center line, and you get a pressure gradient on the soil, which is roughly Gaussian. And because it's broad and not sharp, it's not defined by the perimeter of a jet, it doesn't tend to fail the soil. The soil doesn't crater. But what happens is the gas expands radially away from this low velocity, high pressure, high temperature region, moves radially away, expanding, accelerating, and there is a region of maximum shear stress around in this region on each side. So you get a basically toroidal region of maximum erosion. And here's a side view. This is a nozzle, and this is the lunar surface. And the top is colored to show density, and you can see it's high density directly under the nozzle. Way out here, it's lower density, but notice that out here, as you rise off the surface, the density is getting higher. So sand grains down in the surface may not be lifted too easily. Also, this is velocity. You can see it's low velocity here, but very high velocity out here. And again, through the boundary layer, it's from low velocity up to high velocity. So the challenge in trying to calculate what the ejecta does is to calculate its trajectory through the boundary layers, and then also to calculate the lifting forces down beneath the boundary layer. And once the soil is ejected, here's a simulation that some collaborators did. This is from CFD Research Corporation in Huntsville. they showed, they were doing a simulation of the Apollo 12 Surveyor 3 situation, and this is a side view again with the Apollo 12 lunar module right here. Here's Surveyor crater. Surveyor 3 was just off the edge of the sheet here. But you can see that the ejecta blows in a thin sheet close to the surface. It doesn't blow up at high angles for the most part, but there are some exceptions that I'll mention. And looking at all the videos, you can distinguish certain phases of phenomena. The first square A is before the plume effects. In square B, you can see it's becoming hazy. There's a loss of the contrast. And that's a smooth flow. It's a hydrodynamically smooth flow because the boundary layer is much thicker than the terrain variations. In the lower two frames, you see streakiness forming because it's a hydrodynamically rough flow as the lander gets closer to the surface. Each streak is emanating from a terrain feature. Now in the upper left-hand corner and the upper right-hand, there are large opaque blasts of soil leaving the surface. And this is because the nozzle is close to the surface, because the contact probes are gouging the surface, the foot pads are scraping it, mechanically breaking up the soil. And so you have large bulk quantities of soil being ejected. And by analyzing the shadows, as I'll mention later, you can see that this ejected during this stage is actually going at much higher angles, like greater than 22 degrees off the surface. In the lower left, after you shut the engine off, there's a period of about 20 seconds where there's continuous dust lifting off the surface. This is after the gas has stopped flowing. And I think it's electrostatic because rocket exhaust is charged. It's positively charged. And so it's depositing charge on the surface. And that charge has to go somewhere. And so I think that causes continuous dust lifting for 10 or 20 seconds. And then you can see that after about 20 seconds, it is cleared again. The dust has all moved away. There's a video here. If you could please start the video. So this is Apollo 15, looking out the right-hand window. You can start to see the haziness. Uh-oh. Did it freeze up?
So about what altitude is 15 when it starts to pick up?
I don't remember exactly 15, but it's in the backup charts. They were nominally 23 to 30 meters above the surface when the blowing dust was visible to the human eye. We'll skip the video if we can get it started up again. So let me just mention that Apollo 12 was an exception to the general case. It had vastly more appearance of blowing dust, which I think was really just an optical effect because the sun angle is at half the angle from the other missions. And so therefore the sunlight had to travel through twice the distance to get to the surface and then back up to your eye, so it made it look twice as opaque. It was also, Apollo 12 was an exception that they reported the dust blowing at a much higher altitude than the other missions. Again, I think that was just the optical effect, that it was more visible from a higher altitude because the sunlight had to travel twice as far through the dust. Okay, so we'll skip the video, which is a shame, but I don't want to crash again. So we do identify rocks blowing. Rocks as large as 10 centimeters or even larger are blowing at high velocity. People used to say that rocks would not blow during lunar landings, but we've proven multiple ways that they do blow. Everything agrees large rocks are blown by the lunar module. And we've calculated their velocities, and we've shown by simulation that the simulations and the observations all agree. Also, there were these phenomena that we didn't understand at first. We were calling them dust tails. They would appear for about 2 frames of the video and then disappear. And during some field testing in Mauna Kea, it was repeated. We now know that a dust tail is when a rock begins to get undercut by the gas. So when the rock is sufficiently exposed up into the boundary layer, then the gas gets diverted down and around the rock and it begins to undercut and form a scour pool. And that enhances the rate of erosion right around the rock, which increases vastly, because of the higher erosion rate, it's dumping a lot more dust into the gas flow in that local region. And in the wake of the rock, you have this tail, and the dust tail ends as the rock is ejected. And so from this, we are able to calibrate, it's another calibration of erosion rate, because we can tell the rate that rocks are becoming exposed and ejected, and we know the size of the rock, and so that gives us an estimate of how fast the soil level is being lowered around those rocks. Terrain modification, there are large chunks of soil being blown. This is another thing we recently discovered, this stair step. Back in the Apollo era, this was mistakenly identified as a fissure in the soil, which is it's easy to understand how you would think it's a fissure, because you really don't expect a stair step in the soil. Your mind doesn't want to believe it's that. But this is actually a stair step. It's higher here and it goes down 1 centimeter to this level. And this stair step, this geological contact between geological layers, goes way around over here. And it's not just on Apollo 11, but on several of the missions we've identified this. And here it is on Mauna Kea. We've seen the same thing. These are abrupt stair steps in the soil. And on Mauna Kea, we could identify it was because there was a property change in the soil. It went from coarse to fine to coarse to fine, because these were annual reworking of the tephra, and the aeolian reworking of it was sorting coarse, fine, coarse, fine. On the lunar case, I'm going to go back to that picture. I think there's some really interesting science to understand what is the property change that makes the lunar layers have this erosion characteristic. I'm thinking that there is a thin layer on the, like a 1 millimeter thick skin on each stratum, that is more mechanically resistant to the plume than the rest of the layer, probably some space weathering effect. And here we go on, I think this was 14, where you've got the same layer, and it's in a toroid around the nozzle, just as you would expect, because higher erosion rate is about 1 meter away from the nozzle. We also see these other features. These are unheaded erosional remnants. You can see a little bit of a layer stepping downhill right here as well. This is where the footpad scoured the surface and the contact probe scoured the surface. But in here you see unheaded erosional remnants, which are indications of cohesion in the soil. And it's very difficult to predict erosion rate because of the cohesion. We don't really have a good understanding of that. Another phenomena is the lightning, photometric brightening around the landing sites that was noticed in the Apollo missions, and we also repeated something analogous to that on Mauna Kea. Right where we fired this thruster onto the soil, it left it lightened. But we're not sure that the mechanism here is the same as on the moon, and the mechanism on the moon is not well understood. Okay, so why are these plume effects important? Apollo 12 landed 155 meters away from Surveyor 3, and the astronauts walked over. This camera right here was one of the pieces that was cut off and brought back to Earth, and this lower portion of the camera, shown here, was dissected in part. The rest of it is in the Smithsonian. This entire camera is in the Smithsonian now. But portions were sent out to researchers, and right now I have about 5 or 6 coupons in my lab, including these two, which were on the side facing the Apollo 12 lunar module. Now, this is a bolt hole, and the white area is where the washer protected the paint. And the darkness out here, we were able to show through spectroscopic analysis with EDS and XPS. The darkness out here is actually lunar material. And there's a shadow. There were shadows all over the hardware. This shadow here was the shadow of the bolt head. And all the shadows point back towards the lunar module. And I'll say more about the shadow in a second. This is an SEM image of the surface of the paint. These balls are the paint pigments. And this is the area that was sandblasted by the spraying soil from the lunar module. And you can see there's a lot of surface change in the texture. Also, we could see a lot of lunar material in here. You could identify individual grains of dust from the lunar surface. When we did energy dispersive X-ray spectroscopy, EDS, we were looking for iron, calcium, magnesium, and titanium because they were in the lunar soil, but not in the paint. And so here we took a stripe from the washer out into the dark area, and right at the edge of the washer, those 4 indicators jumped up, indicating that that's where lunar material was. Same thing going across here from lighter to darker back to lighter. You see it goes up in the darker areas. And then the one I want to point out mostly is going from the washer across the dark shadow of the bolt head and then out into the regular acreage. The lunar material is, again, proportionate to the darkness. It jumps up and then it goes back down again. And so that tells us that the washer, the bolt head's shadow is actually composed of lunar material. And that means there was more lunar dust on the Surveyor before the Apollo 12 sandblasted it than there was afterwards. So the sandblasting effect removed lunar material. And that makes sense because dust blowing at 1,000 or traveling ballistically at 1,000 meters or 2,000 meters per second does not stick, it bounces. We're used to dust sticking in an atmosphere because dust doesn't travel that fast in an atmosphere. But in a vacuum, with dust traveling that fast, the kinetic energy is vastly more than the energy of cohesion. So even after you lose some energy in the collision, there's still enough energy to come back off. So the sandblasting scoured the area clean, and that raises the question, why was there so much dust on it before the Apollo 12 got there, which is another question. Also, the surfaces were pitted and cracked. You can see this mud cracking pattern, and there were pits, and the pits are correlated to the cracks and even more so to the vertices of the cracks, which tells us that the pitting caused the cracking. And this is a laser scan inverted of a pit and then a crack radiating away from it. And down inside the cracks, if we focus the SEM down into one of the pits, you can see a lunar soil particle down at the bottom of the pits. So now all the pits were about 100 microns in diameter. So apparently the larger sand particles would penetrate the paint and then radiate cracks away, but the larger dust-sized particles could not penetrate the paint. They just bounced off. So there were two different effects we saw. There was the scouring of the overall surface with greater than 100% surface coverage. It was probably about 300% or more surface coverage. And then the pitting, which just made a finite countable number of pits. From that, we could estimate the quantity of soil that hit the coupon. And we wanted to compare that to the optical density of the blowing dust clouds. So we found, now unfortunately the cameras were film cameras. They don't exist anymore. The film is from a company that doesn't exist anymore. You can't get it. You can't calibrate it. Some of the missions, they're not sure what the astronauts had the camera settings at. Harrison Schmitt reviewed this for Icarus, and he really wanted me to make sure that I understood that they didn't know what the camera settings were. And I had to really convince them, we understand that. And that's why we were very rigorous, and we could only get 3 data points out of all 6 landings because the degree of rigor we had to use to make up for all the uncertainty. And so we had to find a rock that was in the cloud and then not in the cloud in successive frames. And then by getting the bright side and the dark side with the cloud, the bright side and the dark side without the cloud, you can calculate the optical density of the cloud. And so very crudely, we could estimate how much soil was blown during a lunar landing and compare that to the amount of damage on the pits. Now, the amplitudes have been rescaled so they'll both fit. But in reality, it's 100 to 1,000 times more soil was blown than you would have guessed by the number of pits. The optical density predicts there was a lot more soil blowing than the amount of pitting that took place. But the model does accurately predict the right spectrum of pit sizes. So we believe the model is correct. And then how do we explain the discrepancy? Why was there more soil blown than what actually hit the Surveyor? Well, it's because the Surveyor was down inside a crater and the majority of the soil probably went right over it. And so it was only being struck by the particles that scattered out of the main sheet of soil, which was about 1% or a tenth of a percent of the flux of the main sheet. So that actually, now that we realize that's the explanation, it's sort of should have been obvious. We should have never assumed that the main sheet hit the Surveyor, because as I'll show you in a minute, the main sheet is only 3 degrees thick. And so for the main sheet to hit the Surveyor, the terrain at the lunar module would have had to have been very coincidentally tilted at just the right angle to within plus or minus 1.5 degrees, which is not likely. We also did some sandblasting experiments. Ryan Clegg, how much time do I have? I'm out of time? Oh, 2 minutes, okay. So we did sandblasting experiments, and we've shown that JSC-1A, even at very low velocities, can eat right through fabric, including carbon Kevlar weave, and damages glass significantly. So, but where does it go and how fast does it go? To answer that, we've measured the shadows of the lunar module on the dust cloud in order to determine the morphology of the blowing dust. And with a lot of trigonometry, and we went out and actually measured lunar modules that were still in existence to get the three-dimensional geometry of the lunar module, and we've done computer simulations. And the end result is that all cases except for Apollo 15, the dust was blowing in a thin sheet of about 1 to 3 degrees angular thickness vertically, off the horizontal. And the reason Apollo 15 was different, we couldn't get Apollo 12 because with the low sun angle, the shadows were too long, and they exceeded the field of view. But on Apollo 15, the reason why the dust was ramping up at a higher angle is they were descending over this crater. In fact, when they landed on the rim, they tilted back 11 degrees. And so we were measuring this much higher angle because it was coming out of an 11-degree slope, add on a couple of degrees for the lift forces, and that's why you get, 11.8 in that case. We've done simulations of blowing dust particles using computational fluid dynamics, and we get the same agreement. For different diameter particle sizes, different altitudes of the vehicle, it always blows 1 to 3 degrees, and a variation of velocities depending on particle size, altitude, and thrust of the vehicle. So we've done a lot more mapping of these many different cases with different thrusts, different altitudes, with improved modeling, and we're able to repeat the rough and the smooth hydrodynamic flow. And I feel very confident. Also, we're able to match the rocks. We can see rocks blowing, and we're able to pretty accurately match the velocity of the rocks blowing. So I have a lot of confidence that we're getting the right velocities. With those velocities and those angles, the dust literally goes all over the moon. And this is the altitude of the command and service module. And you can see that it crosses. There's 4 nodes where it crosses the ejecta paths. So you have 4 opportunities to intersect the blowing dust. And if you're unlucky enough, I think it's about a 5% chance that you're going to cross it. So 1 out of 20 missions, you're going to get sandblasted on orbit. Or if you have 20 spacecraft on orbit, I got to be really fast here. Yeah. Okay, so what height does the blowing begin? I'm just going to say that 40 meters, you can ask me later about this if you want more details, but 40 meters is a reasonable estimate we feel confident in. How much material is blown? We really don't have a good estimate of that, but using optical density measurements and looking at the shape of the terrain, the best estimate is 1 to 2 tons in each lunar module landing, and it's proportionate for a smaller vehicle. And so we've done these charts for Rob to try to predict the flux based on different Google X Prize thrusts and distances. And so Rob has used this to try to determine a safe landing distance. And that was it. There's still a lot of physics missing. I would like to put in a plug that we need these Google landers to go to the moon because there's a lot to measure there, a lot we want to obtain from the Apollo sites, including understanding the plume effects. There's a lot of physics we still don't understand there. So thank you.
The next presentation. Well, if a picture's worth 1,000 words, you can either watch the charts or I can talk for 40 or 50,000 words. Or not. This is what the moon looks like when it's dark. There we go. Okay. Okay, just to kind of review, this is just a quick map to show you the distribution of the Apollo landings. The Surveyor landings are in yellow, and the various Russian, or at the time Soviet, lunar missions landed. In addition to the way the chart that Rob showed, there's a whole variety of other things that fell on the moon, various orbiters and other debris that's landed there. And so if you include all of that stuff, you get the chart that Rob showed. We're still continuing to collect data. This was acquired last night. This is the Apollo 15 site sitting here looking across Hadley Rill. Next one should, there we go. So here's the Apollo 15 site. They explored down here towards the Apennines and over here towards the Rill. When you actually look at the detailed picture, you can see all kinds of structure in the wall of Hadley Rill. This is an oblique view looking off to the east of the site. So we're still collecting data. Okay, I just want to go through this pretty quick. One of the first missions that was sent to the moon was Ranger, which was designed to take pictures as it approached the moon. We've seen those pictures before. I want to show you how it ended. In each case, the spacecraft crashed into the moon. Ranger 6 was technically successful, but the camera didn't work, so there are no pictures, but we did find out where it landed. These show the individual craters. Craters are about 15 meters in diameter, and they're typical of what you'd see as any small lunar crater. They do have these very nice ejecta patterns, both bright and dark ejecta. And there were a number of surveyors. Apollo 12 went to Surveyor 3. This just shows one comparison for Surveyor 1 of what these things look like at high sun and low sun. You can see a little bit of a shadow extending off here. We'll go through them one at a time. This is the collection. So this is Surveyor 1, 3, 5, 7, and 6 in no particular order. They're fairly small spacecraft. They don't have a lot of structure. Mostly what you're seeing in these pictures are the big solar panels on the top. But we know where each one of those are. Two of them, numbers 2 and 4, were unsuccessful. 2 crashed. Number 4, it's not clear what happened. They lost contact with it, and it may in fact have landed if it just simply executed the rest of its program. If the whole spacecraft just crapped out at that point, it would have produced a crater. We haven't really looked for those yet. So there's not much detail of the Surveyor landing sites. In Surveyor 3, you can see, I'll come back to this when we get to Apollo 12, but you can see their trail. Okay, so let's talk about the Apollo sites. Just to give you a perspective of scale, this is the Apollo 11 landing site and the amount of distance they traversed. There's the Washington Monument. They went 250,000 miles and never even made it to the gift shop. And this has to do some with the thing Rob's going to come back to later in terms of the areas of keep out around things and how in one case, it's easy to say stay out of this whole area and you can draw a simple circle. This is the Apollo 17 set of traverses, it's the same landing point next to the Washington Monument, and the different traverses. And this is clearly a much larger area, and it would be very difficult to sort of draw a circle around all this and stay out of there. And so what the document recommends is a bunch of individual circles around specific items and sampling sites. And Rob showed this picture before. This is what we're looking at from orbit, is the descent stage of the lunar module. This is the Apollo 16 from the LRV camera. This is the Apollo 13 descent stage when it was still on the Earth. These shields up here, which were for the thrusters, you can actually see those sticking up in the shadows in a couple cases. So Apollo 11 landed in the middle of a Mare area, Mare Tranquillitatis. Here's what the landing site looks like. You can see the LEM here. They came in essentially this way. Presumably they were going to land over here, except there's a large rock field associated with West Crater. They flew over Little West Crater and finally landed there. When you look at it in detail, you can see the LEM. You can see the ALSEP. This is the retroreflector. This is where the TV camera was positioned. I don't know that we can actually see that. And then Neil Armstrong walked over here to Little West Crater to take some pictures and came back. So this is a very limited area of exploration. And this is what the scene might look like if you were looking from here back towards the LEM, except this part wouldn't be there, nor would Buzz. Apollo 12 landed in another Mare area in Oceanus Procellarum next to Surveyor 3. This is what the landing site looks like. Here's the LEM. You can see the tracks going out to the ALSEP. They walked around Head Crater, down towards Bench, over to Sharp, back around the south side of Surveyor Crater, into the crater. There's Surveyor 3, not 7, I can't type, and then back to the LEM. This is the close-up. Here's the lunar module, and you can see their tracks. Here's the ALSEP experiments. One of the things that I've been looking for and haven't been able to find are those large antennae that Rob showed. It's not clear whether they're still standing or whether they fell over or whether they've just disappeared. You can actually see in detail the passive seismic experiment has this big aluminum blanket on top, and so it's real obvious in all the pictures, but you can actually make out the individual experiments. You can see where they walked around. This is the antenna. It's not, I haven't been able to find this in any of the shadow pictures where you've got a long shadow. So I don't know whether it's disintegrated, fallen over, or we just haven't recognized it yet, but it might still be something there. So if you were standing over here looking across the Surveyor crater, you'd see the lower half of the descent module and possibly the antenna. Okay, Apollo 14 landed in the Frau Morrow Formation right in the center here. When you look at it in detail, landing site is down here. They put the ALSEP over here, and then they hiked up in an attempt to actually get to the rim of Cone Crater. And it's hard to see in this particular version, but we can actually see the entire trek up here, and they were really close. You know, it's just a matter of the local horizon, I guess, being in the way, but they really were very, very close to the rim when they turned around. A little bit close up, here's the LEM. You can see the tracks going over here to the ALSEP site, and then on their way off to Cone Crater that way. You can see the individual experiments. The lunar retroreflectors are all pretty obvious. In one case, there was a plastic cover on the retroreflector which was laid down next to the reflector, and you can actually see the reflection from the piece of plastic. So at least that, I don't know what it was made out of, but at least that material is still there and capable of reflecting stuff. There was a seismic array where they had a thumper went out this way. So the tracks are all very, very obvious. Wherever they walked, you can see an obvious track. And so at least from a space weathering perspective, those are all still visible. Again, this is what if you were to be looking this way, here's the ALSEP, and all these little tracks that they made, and all these little cables and stuff are all still there. In one case, one of these cables was actually lying perfectly flat on the ground. It was a ribbon cable, and right now it reflects, when it's noontime, you can see it from orbit because it reflects so much sunlight back. Here's 15. This is the view looking over this way I showed you at the beginning. Apollo 15 landed over here on the east side of Hadley Rill. Here's the LEM. Here's the LRV where they parked it after they were done with it. Here's the ALSEP site with all the different experiments. You can see in detail, you know, the big obvious seismometer. The other instruments, you can see, you can't actually see the heat flow probes, but you can see where they actually drilled the holes from the disturbance. The retroreflectors over here, you can see where they put it. All these are detailed now. Part of this is important because a lot of this stuff was approximately known. I'll show you an example later on, and now we know exactly where everything is, including sampling sites. This would be what you would see if you were standing over here looking back, except again the top of the lunar module would be missing. 16 landed in the Descartes Highlands. Here you can see they too came down near the edge of a crater. Here's the lunar module. They parked the LRV over here. They put the ALSEP site down here, and they also did a seismic profile out here. Again, just a close-up of the ALSEP equipment. And this is what the seismometer looks like. It's got this aluminum foil cover on it, and it's still bright enough to reflect a lot of light. So not only is the aluminum still there, but it's not coated with much because it's still a bright reflector. Apollo 17 landed in a valley here on the Mare material, and they traversed across much of the valley. Here's the lunar module. Here's the ALSEP site over here. And then they did an electrical properties experiment over here with this big cross of cable sensors they put in, and they parked the LRV down here when they were done. So in this last slide, this is geophone rock here. Here's that same rock from the surface looking towards the south along the seismic array. I just want to show you a couple examples. This is the station 6 Boulder. They drove over here, parked here, and then explored the boulder. Zoomed up, you can see the individual pieces of the boulder and the scour mark it made as it came down the hillside. And when you compare the orbital pictures to the surface pictures, this is looking from the north to the south, and this big mass here is this piece is the piece up here. Similarly, if you look from the side, you can see the individual pieces that are obvious in the surface photography, you can see in the orbital photography. This is just an example of when you compare the maps that were made during the Apollo era with what we actually see from orbit. There's some differences. I mean, not the to say that they did a bad job on the mapping. It was hard to judge where things were. But this allows us to put better perspective on where the samples were. I took the map and centered it on this piece of the boulder, and you can see that the tracks are approximately in the right place, but this crater's not quite where it's supposed to be, and the rocks are not quite where they are with respect to each other. But now we know where they are, and we can get a better understanding of where the individual samples were and what the local geometry of those samples were. Similarly, this is Shorty Crater. This is where the orange soil was found. They sampled along the southern rim of the crater here. This is the same kind of thing. This map just overlaid the boulder on top of the boulder, and then you can compare some of the other stuff. The geometry of the crater in this little cartoon is a little bit off because underneath it you can actually see is where the tracks are. So they parked right here. They walked over here. Jack found the soil over here. Meanwhile, Gene had gone over here to take a panorama back across the crater, and this is the view. So you can see where the rover was parked here. This is where the orange soil is. Here's that rock that was in the last picture, and in this picture you can't see it, but you can see that where Cernan walked over here to take the picture and where he walked back. Now, the one thing about the LRV traverses is it's very difficult to almost impossible to see the wheel tracks of the LRV. Right around the lunar modules where the surface was brightened, that Phil alluded to, they're very obvious. Once you get outside that area, it's difficult or impossible to find them, even when you know where they should be. I mean, we know exactly where the rover was parked. It was parked right here. You can see all their footprints from them working around the rover, but there's no obvious track anywhere. Only in a few places can you see that. On the other hand, the Soviet Lunokods, which had about the same loading as the LRV did when the astronauts were in it, the tracks are incredibly obvious, and that's because they had grousers on those wheels, which ripped up the regolith a lot more. The other thing of interest were the S4B craters. The S4B was the upper stage of the system that put them into translunar path. This was subsequently crashed into the moon for a seismic experiment. These are the kind of craters it makes with these kilometer-long rays. This is the collection of craters. There's one missing, Apollo 16, which we haven't found yet. These are kind of neat because they have this funny-looking mound in the middle, which is not what you would expect. These craters are about 35 meters across. This is kind of important because this is relevant to the LCROSS experiment. LCROSS crashed a booster into the surface, and so it's important to understand what the cratering dynamics of a tin can are when it hits the moon in terms of excavating material and throwing it up. Now, we don't know what this looked like at the time in terms of ejection dynamics, but at least we can see what happened at the end. It gives us some guidance on what the LCROSS crater might look like. Okay, some of the things that I guess Rob's going to come back to later are the so-called keep-out zones, and I just wanted to illustrate a couple of those. This is the Apollo 11 site, and the nominal radius is 75 meters, so it includes all the traverses and extends out here just beyond where Armstrong went to Little Rose Crater. This illustrates some of the problem with all the sites. The landing site for Apollo 15 is up here. These are just for notation purposes, the dimensions of these circles. But, you know, there's a couple stations up here, there's a station here, there's two stations down here, there's one over here, there's a couple down here. If you can't just draw a circle around all this, but presumably we can identify each of these particular locations and illustrate where it is and what the keep-out zone would be around that particular station. Similarly, this is the Apollo 17 site. There's a 2-kilometer radius for overflights and landing around it. That's what that looks like in a low-resolution perspective. When you zoom up, here's the LEM is sitting here, and this is what a 2-kilometer radius circle is around here. Most of the stations are outside of that area, and so they're scattered all over the valley. And so similarly, they would have to be identified. We've found all the stations, but you'd have to identify them on a map. And this is Apollo 17. This is a 225-meter keep-out radius, includes the LEM, the LRV, most of the electrical experiment, and the ALSEP package. This is a little bit off the tack here, but I just want to show you some of the Soviet missions we found. The sample return, one of them was the Luna 20, landed in the Highlands. You can actually see the vehicle here, and this little shadow sticking off here is the arm that put the sample in the Earth return container. Two of them were sent to Mare Crisium, Luna 23 and 24. 23 failed, 24 was successful, and so the entire spacecraft for 23 is on the surface, and only the lower stage of 24 is there. So here's 24 sitting here on the rim of a small crater. The fact that it's actually sitting on the rim of a crater partly explains why the samples, when they were brought back, weren't what they were expecting. It's because it sampled material in the ejected from this crater from a deeper horizon than this is actually exposed over much of the surface. 23 is sitting here. Even for the small robotic missions, you can see the same bright plume around the vehicle. The other thing which Phil didn't mention is that directly underneath the vehicles, it's dark, as if all the fine-grained stuff that is very efficient at back reflecting has been gone. Now, I don't know either why this is brighter, but you got a dark area, a brighter area, and then it goes back to normal albedo. There's a big white thing right next to the vehicle. It may have been a rock, and maybe that's what happened. It hit the rock because they were in communication with it, but just couldn't acquire a sample for some reason. Lunacods 1 and 2, we found the landing sites. They're not. Here's the lander. You can see when they drove off and wandered around the lander before they went off on their excursion, and ultimately they drove over here and finally just crapped out here. The neat thing about this was there's a laser retroreflector on Lunacon 1, which was originally tracked during the mission, but they lost it. And when we found it, we sent the coordinates to Tom Murphy, who went to Apache Point and found it again with the laser retroreflector. It's very bright, and now it provides a point off in the northwest part of the moon to do the geodetic experiments. This just illustrates the landing is over here. They went on a traverse to the south, came back, passed the lander, and went up to the north, did a big loop around this crater, drove up here, and then the mission finally ended over here. They went into this crater and almost ended the mission there. They got stuck in the loose material on the interior crater wall, and they finally managed to get out. But that's one of the problems of not really understanding before you get there what the physical properties of the soil are. And it was remotely controlled, so they didn't really have the perspective that an astronaut did, where you could see something going wrong immediately and stop. Lunacod 2, same thing, was a lander. Okay, 2 minutes. All right, well, that's good. You can see the tracks here, and it finally ended over here. There's a rill over here that they managed to get across and drove up here and finally ended. This makes an interesting point. The Soviets, I guess, sold this rover to Richard Garriott, the son of one of the astronauts, for $68,000. So apparently this is now his property. And that's the end, literally and figuratively.
So based upon the analysis that Phil had and what Jeff's had and some other analysis, we, within the agency, came up with a three-part package, a recommendation package for descent and landing for mobility and contamination, and then 2 appendices which deal with how we might assess these sites from an engineering and science viewpoint. So let me start the little timer here. So actually, we just didn't concentrate on the Apollo sites. We have included 3 sites on the moon relative to this effort. One that deals with the 6 Apollo sites, but we also included the other unmanned landing sites, and we'll talk about why a little later. So we included Surveyor within the recommendation package and how we treat that, but we also looked at the impact sites. Jeff did a great job of briefing the impact sites from the 3rd stage of the Saturn V, the S4B. Those impacts, as well as the Ranger impact sites. So all of these have been included in the recommendation package that we're showing. So the task was twofold. One was to how we could preserve and protect these sites from visiting landers with initial capability that we think has good probability in late 2013 for unmanned landers potentially visiting these sites at that time period. And then secondly, we wanted not only to preserve and protect, but how do we assess these sites once we get there from an engineering perspective and all lunar science. A key premise here is that this document doesn't deal with any other international hardware. It is only focused on assets that belong to the United States government. So basically the NASA hardware. Within that context then, there were a couple of premises. One is that this is a living document. We plan to continue to mature it, to grow it, to add to it over time as we get smarter with analysis and as technology changes. And secondly, it was based at this point on the current understanding of the architecture of the landers and the robotic capabilities. In other words, they're not going out to grab and pull samples. The basic data collection is high definition and stereoscopic imaging within the rovers. So we developed actually four packages, sections. One that deals with authority and definitions, especially relative to the boundaries, how we deal with risks associated with descent and landing for trajectory guidance and navigation. Once we're at the surface, how we deal with the risk associated with mobility, and then relative to contamination in a number of areas associated with that. So what I've done is pulled a number of the key recommendations out of this package to brief to you today relative to this. The first thing is to note is that this is really new ground relative to the agency. There is no precedent within NASA over the 50 years of human spaceflight that deal with going back and visiting historical sites or archival hardware. So this was the first time that we've ever had this issue pop up within the agency that we've tried to address with this package. Secondly, is that all of us know within NASA we deal with a lot of requirements and guidelines and constraints, very specific details. This package is different, however. We deal only with technical recommendations. There's not a legal requirement or technical requirement that a visiting vehicle must meet. So these are best is collective wisdom or knowledge capture with data associated with it, but specifically they are recommendations based upon technical data. And then third, it was important to note that the United States government still legally owns all these assets that are the flight hardware sitting on the surface, to include the Apollo artifacts. So in section 1, we dealt with some definitions. In terms of descent and landing, what kind of boundary condition would we want? So we looking at Phil's data and the fact that especially the small micron-sized dust can get up to 2,000 meters a second and could be extremely destructive to these sites. We set the descent and landing boundary at a 2-kilometer radial distance from the site, in this case from the descent stage. For the Ranger sites and the S4B sites, the impact sites, we put a 0.5 kilometer distance. Relative to those sites. Then we dealt, coming on in, with constricting boundaries. The next one dealt with what we call the artifact boundary, and that is a boundary condition specific to each site that contains all the artifacts within that. The descent stage, the instrumentation, the rover, in some cases the flag, whatever is there, what boundary encompasses all the flight hardware. And then we go down one more level, and we call it the visiting vehicle surface mobility boundary, and that defines specific keep-out zones or bubbles as a function of each individual instrument. Ion detector, the passive seismic experiment, the lunar rover itself. So we went down to specific levels based upon the imagery that we really got out of the narrow-angle camera and the great work that Jeff's done. We also had a suggestion, recommendation to the visiting vehicles that they have some type of reference or coordinate system. And so we, within NASA, the work that Jeff and Mark are doing with LROC, the work that Mark Nall is doing with lunar mapping and modeling, are working with the teams on a geo-coordinate system to provide some kind of navigational frame of reference relative to the sites for trek planning and execution. So then we moved into areas associated with the specific risks of descent and landing. And there's a significant amount of work done in here. A lot of it is predicated on the 10 years of analysis that Metzger has been doing over Kennedy. The first one dealt with the approach path, that we want all the landers to come in tangential to the landing sites, and there be no overflight associated with that. And the reason for that is threefold. One, we didn't want to get a kick-up of dust that could be deposited at the heritage site itself. One, we want to minimize the collision potential from any vehicle failure anomalies as they come in through the approach, descent, and landing phase. So again, a reason for them to be tangential to that. And then the other reason is that we want to protect the vehicle and the sites at each Apollo site from the high velocity impacts that Phil's modeling shows, these 2 kilometer a second velocities that the micron-sized particles can come up to. So that led us to a recommendation relative to descent and landing associated with the targeting and ellipse and nav dispersions associated with that to target 2 kilometers away, and that has to include the 3 sigma dispersions associated with the trajectory and nav accuracies. But the whole intent of those 3 rules was to put the lander over the horizon. The horizon is roughly 1.8 kilometers away from any spot on the surface. And so by going 2 kilometers away for the targeting, we assure that there's no line of sight to the descent engines and this extremely destructive ejecta sheet that Phil's analysis shows that goes, in some cases ballistically at the moon. It keeps that 1 to 3 degree elevated sheet that's at 2,000 meters a second out of any line of sight with the flight hardware. So Jeff just showed you this. Based upon that recommendation, this would be the 2 kilometer radial boundary for Apollo 17. The descent stage is right there in the middle. We also addressed the architectures relative to these landers and braking burns associated with that. A number of the mission design architectures for these vehicles and lander systems deal with staged deorbit. In other words, similar to Surveyor that had a star solid rocket motor, it took out most of the descent trajectory, then they jettisoned that spent stage and sent it on a ballistic trajectory into the moon while the rest of Surveyor came on down. So a number of the teams are doing that as a staged deorbit and then discarding the primary descent stage that does the deorbit burn on a ballistic trajectory. So again, we wanted not only to cover the lander itself, but any of the braking stages associated with that so that we don't have these ballistic stages coming as overflight hardware that could collide into the site or damage it within dust. So then we got into some discussions of once you're at the surface, what would be some of the recommendations dealing with mobility? So one of the recommendations we took to the administrator recently and was accepted is to provide special significance to Apollo 11 and Apollo 17. Apollo 11, of course, being the first flight of humans to the moon. Some said in here our nearest near-Earth object. And of course, Apollo 17 being the last human visit within the Apollo program. And so we're recommending that we provide special significance to these 2 sites, and that is not unlike other archaeological sites where you don't open up the entire site to exploration and artifact recovery, that you protect some of these areas for future investigations. And so based upon that premise, we recommended that at the Apollo 11 site, we put a 75-meter radius around the descent stage. For Apollo 17, 225 meters radial distance away from the descent stage. Again, Jeff showed you some great imagery that showed that. This is the NAC imagery showing the descent stage from Apollo 11. It's interesting that we see the 3 footpads here very clearly in the NAC image. We don't see the one at the base of the ladder. It's either covered with lunar dust, or this was also the dumping ground for a lot of the camera bodies, the portable life support systems, the liquid garments, etc., the food bags that were jettisoned prior to lunar ascent to improve ascent performance. This shows the angle that showed Neil and Buzz back in July '69 from the camera. We show here the lunar retro reflector and its associated cover, the passive seismic experiment. And then we can see where the Neil and Buzz, Neil in this case, went over Little West Crater and has punched through the upper millimeters of the dirt, exposing darker material beneath the soil. And of course, this is the planar view showing the same view that we see in a bird's eye view for Apollo 11. So as Jeff showed you, this is within our recommendation package, a 75-meter radial distance for Apollo 11. And in this case, for Apollo 11, it protects not only all flight hardware, but it protects all human activity for that flight. It doesn't mean that people can't go up to the artifact boundary and survey within that. They have to land 2 kilometers away and then rove up to it, but they cannot. We're recommending they never go within this circle, and that way they don't roll over Neil's footprint. Here it is for Apollo 17. The LRV was parked to show the ascent of the ascent module, 138 meters away from the descent stage. About 190 meters away were the individual ALSEP experiments, and one of the experiments that Jeff talked about is a couple of 100 meters away from the descent stage. So that allowed us to put a 225-meter radius around the descent stage for Apollo 17, again recommending that this artifact boundary not be intruded upon so that we protect this site for the future. But that said, we really do want to get up close and personal to a lot of this flight hardware. So it said we'll open up 12, 14, 15, and 16 to specific visits to these sites. Because our desire is really to get some great science and engineering data associated with this exposure of the lunar surface over 40 years. So for the descent stage, we put a 3-meter boundary around it, and each of the different artifacts dealing with the LRV, the ALSEP, sampling sites, a 1-meter boundary, as well as any of the peripheral artifacts, the rake, the drill, the storage bag, the flag, a 1-meter buffer zone is associated with that. But what this also said was outside the boundary, we're not going to protect every footprint, we're not going to protect every rover track all over the moon, that it just didn't make sense to do that. So we also have had a significant amount of discussions over the last months dealing with the Lunar Laser Retro Reflector. There are 5 of these active experiments still ongoing at the moon, dealing with they're at Apollo 11, 14, 15 at the 2 Lunicog sites, Lunicog 1 and 2. And so, you know, there's been this debate about whether we're seeing a performance decrease of the reflectance over time. There's some data that indicates we have, other people don't believe it exists. But if it is true that we've seen some reflectance change, some decrease over time, why is that? Is it because there is some small deposit of dust over time over the 40 years? Is it due to thermal deflection within the instrumentation itself? And so one of the things we want to do within NASA is actually get up and take a look at that and see if we can discern through the high definition imagery what is causing that. But we're also recommending that they never do a direct approach to the LRRR so that they don't inadvertently bump into that. But I can't emphasize enough the importance of not doing anything that would degrade or impede the data that we get from these active instruments. So we've had a lot of discussions on how to specifically do this risk versus risk trade of visiting the different LRR sites. For Surveyor, that sticks above the surface. We treat that as another landing site with a 2-kilometer distance, but a 1-meter keep-out zone so that you can rove up and close to that. You know, the interesting thing from the Apollo sites to Surveyor is that the Surveyor sites have not been subjected to a subsequent ascent like the Apollo sites. So perhaps the dust deposition and science going on over 40 years at the Surveyor sites could be uniquely different than what we saw through the blasting effects from the ascent at the Apollo sites. And then we dealt with the Ranger and the Surveyor and the S4B impact sites. As Jeff showed the other day, the morphology of this cratering is uniquely different. This shows the S4B impact site for Apollo 14, which was about 30 meters by 30 meters. And originally we were going to treat this as a large keep-out zone, but then we thought, you know, that's not how we do Mars exploration rover. You know, on Mars we actually go up to the craters, we rove around it, we look inside, decide the best entry path, and then we go down into it. And that's the approach we took essentially here, is that you can go up to the crater. This circle is just to designate where the impact site was, but allowing the rovers to go up to it and then assess and then go into it, but we don't want them to touch any remaining hardware that remains or debris from the impact itself. So then we got into the rovers versus hoppers, and because rovers can go relatively slow, we've seen that at Mars, and minimize the amount of casting or throwing dust, we're allowing them to go up very close and personal to each of the individual artifacts for 12, 14, 15, and 16. But one of the things we came up with is that we don't want them to stay in there overnight. If they go into a lunar night and try to survive and go the next day, we want them to leave, and same within the mission. And the reason is that we don't want to get stuck with potentially high energy events like springs and battery venting that may occur that could contaminate the site over time. So when you die, we want you to die outside the site. And then again, we want all tangential targeting to each of the artifacts, and that way if there's a fail to stop command or delayed stop command or software is not working right within the mobility, we don't have incidences where they bump or move or impact into the artifacts. And then we associated one with backtracking. And this was dealing with the idea that we want to minimize the disturbance within all these sites. So pick an area that you want to enter within the artifact boundary, go in there and exit the same way. So for you golfers, this is the wet golf course rule, right? Well, on the wet golf course, you go along the cart path, and then you go 90 degrees over to the golf ball, and you come back 90 degrees back to the cart path so that you don't do big weavings all over the fairway. And so this is the cart path rule, essentially, for the rovers as they approach into the artifact boundary and the individual instruments. Hoppers are a different configuration for us. Just like the MER type of landers, we want everybody to land, do descent and landing 2 kilometers from the site. But that's me. So, but they represent a unique difference, and you've seen Mazda and Armadillo where it's flying Mojave and it kicks up this dust, and so we don't want any mobility or hopping within these boundaries where it kicks up dust and potentially damages these sites. And so we said, all right, so how can we get them an opportunity? What's an alternative solution that allows them to survey and provide imaging to the sites? So what we did was came up with a low altitude flyby option that allows them to ascend after touchdown and landing. You heard a briefing on that yesterday, up to 40 meters, which is a threshold that we think that we don't see any interaction between the engine exhaust and the very fine particles at the lunar surface. And then they can trek within the artifact boundary, taking imagery, and then land outside the boundary, the descent and landing boundary again. So we preserve the site, but it provides them an option to do imaging at the site, whether that's an impact site or a lander site. Within contamination, we didn't allow any touching of any of the hardware. We don't want them to do any inadvertent dusting, either in mobility or in landing. And also, we dealt with the idea of unburned propellant. All these, whether monoprop or dual prop, have unburned droplets that form within the exit cone that could put toxic material within the site. So out of that, any flybys or on descent and landing, we want to make sure that we didn't have any toxic propellants that could further degrade the site over time. And then the last part was that with Greg and NLSI, we have had discussions with the teams dealing with a participatory science program, both in pre-flight planning to look at rover treks and areas of specific scientific interest, as well as a real-time execution role, similar to what we had in Apollo in the multi-purpose support backroom, where the geologists could provide real-time input in areas of interest. So a pre-flight planning phase and a real-time execution phase for consideration within these teams. So the forward work is that this is an evolving document as lander capability matures and technology improves, and going to these sites down the road will change the document. We're looking at doing much more modeling and flight tests, including getting early data from the flight phases of the Google teams in the next few years that could go into Phil's modeling, see if we can reduce the 2 kilometer distance. We're assisting them with the geo-coordinate system relative to the frame reference for the treks, and then we're looking at a participatory lunar science program that Greg is leading out of the NASA Lunar Science Institute. So with that, let me then turn it over to the assessment piece, and I think, Mike, you're up first. I'm sorry? Yeah, no, I just didn't show everything. So it's in the package, and it says basically that, you know, you have to abide by the Coast Bar, the planetary protection, which is very basic for the moon and not a big threat. But we have it in there. I just didn't show all the package. Let me come back and we'll take it all in the panel if that's okay.
I could try to describe all the pictures that I have. Well, I'll get started while he's bringing it up. I have a few words to say that are on the title page. I'm Mike Squire. I am with the NASA Engineering and Safety Center. And there are about 1,000 individually cataloged man-made items on the lunar surface just from the Apollo program. And that stuff's been sitting there for 40 years, sitting in the lunar environment. And now with the Google Lunar X Prize, we have an opportunity to go back and take a look at that stuff, see what's happened to it, what happens to man-made items when they sit on the moon for 4 decades. What happens? What are the effects of the radiation and solar particles and 500 day-night cycles? What is the threat from the micrometeorite environment at the lunar surface? So I formed a team with the NASA Engineering Safety, and we were tasked to treat all of these lunar artifacts as witness plates to the lunar environment, long-term exposure in the lunar environment. And the team we formed, which you'll see there on the first page, consisted of several engineering discipline experts from across the agency, across the country. And we came up with suggestions, recommendations on which artifacts would be the most fruitful to go look at, why, what we could look at. And I guess we're ready to go. So the approach we took, we were looking at this from the point of view of the Google Lunar X Prize candidates. So our assumption was we would only have high-definition cameras available. That was their only requirement as far as instrumentation. They had to have high-def imaging. So we were assuming no other type of instrumentation would be available for us. So we're just talking about visual data. We used the Apollo 15 site as our baseline. We mostly considered the hardware from Apollo 15. Apollo 15 was the first J mission, so it had the lunar rover. It had a full suite of ALSEP experiments that you see there. Of course, we considered the descent stage and a variety of miscellaneous hardware that were left on the surface by astronauts Scott and Irwin. And as Rob mentioned, our results are contained in a appendix in the report. And we went through and we looked at each of the major items of hardware and made suggestions and recommendations based in these 5 categories that you see here. The first one is materials. Probably the most broadly applicable category is materials from the standpoint of what kind of visible changes have different materials undergone, and what materials would be considered to be more robust in a lunar environment than others. That chart you see there on the right-hand side is just a sampling of some of the different materials that you can find at the Apollo sites. Also, micrometeorite damage is very interesting little subcategory, both from the standpoint of what materials can handle the meteorite bombardment better than others, and also so that we can update our understanding of the current meteoroid environment models. Looking at different structural mechanical systems, we can look for visible changes in any warping where similar metals come together, evidence of thermal fatigue. Thermal protection, almost all of the hardware has some sort of thermal protection system, be it thermal coating, MLI, reflectors. So there's a lot of interest in how those thermal systems have degraded over the years. Of course, dust. All those artifacts can be considered as witness plates and possible targets for dust deposition if there is some dust movement. We can look at maybe differences in dust deposition on conductive versus non-conductive materials, different orientations, vertical versus horizontal faces, and then blast effects, the effects of the ascent stage, what it did to the nearby hardware around the site. So we went through each of the major artifacts, and we'll go through here and kind of point out some of the suggestions and things we were thinking. And if I were to go to the moon, one of the first places I'd check out is the rover. The rover has a variety of different materials, from the thermally coated aluminum frame. The seats are made out of nylon webbing. The fenders are fiberglass. The wheels are actually piano wire, zinc-coated piano wire with titanium treads. So you just have a whole bunch of different materials to sample from. Plus, you have different major components that are attached. You have the antennas that you see there. There's a camera up in front. There's a lunar communications relay box there at the very front. So a bunch of different items to look at the rover. More rover views here. You can look at different structural systems where dissimilar metals come together, and structural components such as the suspension. You have flat surfaces that might be conducive for looking for meteorite damage or dust deposition. You have the control and display console there on the right-hand side. Are the gauges still legible? And if they are legible, what are they reading? And you have all the ALSEP experiments at the site. The design for the ALSEP experiments was they needed to be operable for a minimum of 1 year. So you may consider these a little more robust than some of the other artifacts on there. So maybe that we might see some sort of factor in that standpoint. This is the central station. It has the thermal curtains there on the side, the MLI thermal curtains, the reflector there in the front, which is an aluminum coated thermal reflector. All of the central stations from all the sites experienced a gradual increase in operating temperature. So maybe by looking at the thermal protection, you might be able to get some insight in that. See the cables going there, the Kapton cables. How did the Kapton survive? A lot of the Apollo photographs show the bright, pristine-looking Kapton, so we have a lot of good comparison. Here is the passive seismic experiment we saw in a couple other charts previously. That aluminized mylar thermal shroud there is about 5 feet in diameter. The PSE for Apollo 15 and Apollo 16 both experienced some thermal control problems. So is the shroud flat against the surface? Was it disturbed maybe from the blast? On the right-hand side, you see a close-up. That's a sun compass and a bubble level, which several of the experiments had to help align the experiment. It would be interesting to take a look at that, see if you could get a reading, and compare it to the Apollo reading, see if there'd been any movement, any shifting over the years. A couple of more experiments here. You got the lunar surface magnetometer on the left-hand side. The solar wind spectrometer there is on the right, and it has this kind of radially symmetrical aspect. It has those 6 different faces. Each one is facing a different direction. And if you can get close and look at each of those faces around, you might see some differences in meteorite damage or dust deposition or degradation, and get some sort of directional component to some of those mechanisms. Here's the retroreflector, which Rob discussed. There do seem to be indications from some sources that there is some long-term degradation on the retroreflector. So is that caused by dust? Is it caused by meteorite damage or some other mechanism? Would be very valuable to find out. Here's the RTG. The half-life of the plutonium in the RTG is 89 years, so it should still be producing energy. It also has this radially symmetrical configuration, and it has these vertical graphite, beryllium fins, which you don't have many vertical surfaces like that. You might see if there's any deposition, any meteorite damage. And again, you might be able to get some sort of directional component by looking at the different fins and comparing them. Here's the descent stage. If you've seen some of the old video of the ascent, you see all kinds of pieces flying off of the descent stage. So it'd be nice to take a look and get a good view on what kind of damage it actually sustained during the lunar liftoff. And as Rob did mention, part of their mass offload prior to leaving the lunar surface, they unloaded all their extra equipment, their extra clothing, food bags, all that stuff was jettisoned out the airlock and deposited right next to the descent modules. That should still be sitting there. And then there's miscellaneous smaller items. You have tools, rakes, core. You have these packaging items that you see scattered all over the place. That's not even included in the itemized 1,000 item total, but they would give different material aspects to look at. In the upper right-hand corner is the gnomon, which is that little skinny thing next to the astronaut's leg. That's a vertical reference, and it also had a grayscale and a color scale for photo processing. What has happened to the colors and the gray? Has it faded? We have good photography to compare it to if it has. The primary life support system, which is the backpack the astronaut there is wearing, that's part of the pile of stuff that was offloaded next to the descent stage. Also his lunar boots, liquid cooling garments. We did talk about the flag. That material for the flag is off-the-shelf nylon. It wasn't special nylon meant to last, so it would be very interesting to see what is left and what that flag looks like. There's the Falcon Feather. These are more on the human interest side, more than really pure engineering, scientific study. The upper right-hand corner is the plaque to the fallen astronauts and cosmonauts from Apollo 15. And Apollo 16, Charlie Duke left the little family portrait there. And then this is Rob's favorite picture. If you look in the center, yeah, I guess I'll use the pointer. look in the center of the crater, right here, and there's an inset. You see a little white speck. That is, that's Alan Shepard's golf ball. And this picture was taken from the limb, so you see he really didn't hit it all that far. This thing right here is Ed Mitchell's Javelin that he made using the handle from one of the tools, one of the scoopers. So this might be at least interesting to go see if you could find the golf ball in the sand trap. You know, we're not really going to know what is interesting or valuable until we get there and take a look at it. And one of the suggestions that Rob discussed is to have a team ready to support real-time the ground controllers, like the back room and during Apollo. So that's something I think would really be important. And I think that's my last chart. Yep. Okay, thank you.
Hi again, I'm Barbara Cohen from NASA Marshall, and I'm here to talk to you about the science assessment or science opportunities from this scale of mission. Again, here's this document that Rob's been telling you about. I'm going to tell you about Appendix A5 science elements. This is a science assessment that originally I think some people thought would be a good League Special Action Team opportunity. But then due to various constraints, it was constrained to NASA civil servants only, and people sort of said, do we have any lunar experts within NASA? So it turns out we do. So this is a committee that was headed by Wendell Mendel at JSC, a couple people at JSC, Gary Lofgren, John Gruner, and Dean Epler, and Sarah Noble, and Noah Petro at Goddard, and me at Marshall. So we reviewed and contributed to the draft document with the suggestions for keep-out zones and issues like that. And then we suggested potential science that could be achieved by revisiting the Apollo sites and impact sites. In this document, we assumed only the lander, rover, hopper missions, the Google Lunar X Prize size missions, equipped only with their normal sensors, optical cameras, normal telemetry. We don't define or prioritize science that could be achieved by carrying additional payloads. There's lots of opportunities out there to carry additional payloads and get really interesting science. Those aren't within our purview in this particular document. And we don't include any of the engineering measurements of interest that Mike just described to you. So these fall into sort of a couple broad categories: observing the science hardware, not with an eye toward observing the hardware itself, but with an eye toward understanding the measurements that we've already made. Some of them depend on how the science hardware was placed. Observing the surrounding terrain, again, to understand the measurements that we've already made, including the samples themselves, to gain context, and new science opportunities, new measurements that you might be able to make. So lunar laser ranging retroreflectors, as several people have already said, and you've heard a couple times during this conference, they're active experiments right now, so it's really crucial to the science community that these not be disturbed. They're very sensitive to disturbances. We don't want to degrade them by dust deposition or compacting the soil around them. But as several people have already said, of course, the signal may be degrading over time, and we're not sure why. It could be due to micrometeorite impacts into the surface, could be to dust settling on the surface, we're not sure. So the suggestion that we make is to image the current state of the retroreflector surfaces. This would take some pretty high resolution imaging, but it's certainly doable. Observing some of the other ALSIP experiments, these are not currently active, but when we analyze the data from them, the Royal, we analyzed the data from them, it showed that accurate interpretation of some of these data depends on the local terrain. In the case of the heat flow probes, when the astronauts placed the heat flow probes and then stomped on the soil around them, that changes the properties of the soil. And the heat flow probes are sensitive to one of the inputs into the modeling is the compaction of the soil. So by stepping on them, they've changed the compaction of the soil. It's an important input into the models. So documenting the current state of the heat flow probes after they've been stomped on. The LEAM and the lunar dust detectors, both of those had signals that were enigmatic, that we don't fully understand. And so documenting their current orientation, documenting the dust buildup on those, and to see if there's sources of dust around them would be an interesting experiment. Again, we don't have any purview over the Soviet Luna missions, but there were several sample return missions. If someone were to go to these and document their geologic setting, they've been observed with the Lunar Reconnaissance Orbiter, but they haven't been observed in situ. The samples that were returned don't have a full geologic context associated with them. These were single point landers, they weren't rovers. So going and documenting the surroundings of these sample return missions, maybe even multispectrally, would add a lot to our understanding of the geologic context of the samples that we have in our collection. The sampling stations themselves, there wasn't a great deal of interest from this group in protecting every sample site, or even of revisiting most of them. There are some things that you might think about, particularly with samples that were acquired from boulders. There were pictures taken before and after the sample was acquired from the boulder. So maybe going back to some of those sites and re-imaging the place where the sample was knocked from. Maybe you could see some changes there over 40 plus years. Someone mentioned before about the orange soil, and there's a picture of it there. That was just a single point collection of orange soil. We were not able to document the extent of the orange glass deposit. You heard earlier about how the volcanic glass beads have water within them, and they're telling us about the magmatic history of the moon, the volatile history of the moon. They're really important samples. So that's something that you could consider in these special cases, going back and looking at those sampling sites more. But moreover, if there's a visit that someone's making to a sample station from an Apollo site, it really is a strong recommendation from us to interface with the science community, possibly through some of the mechanisms that have been proposed, to understand whether any additional desires come from the science community for those particular sample sites. Sites of impact by spacecraft and parts of spacecraft, I've already showed you some of these. There's no specific keep out zone associated with these. You can drive right up and drive around, and we certainly encourage that. These are young, fresh craters of known age and known impact energy. And so these are important parameters for us for understanding how craters form and evolve. So when you're driving around them and looking around, these are the parameters we're interested in: the morphology of the crater, the depth to diameter ratio, in particular, the shape, the nature of the ejecta blanket as a function of distance, whether it's discontinuous, whether it comes out in rays like you can see here, what does it look like from the ground, and the nature of the target material. Is it bedrock? Is it fluffy? Can you see layers inside of it? Those are all important things for understanding the impact craters themselves and the impact cratering process. Dust levitation and settling. This is something that the engineers are very interested in too, so this is a nice crossover between science and engineering. There have been several measurements that say that possibly dust is levitated. There are some models now that suggest that it should be, but we don't have any direct, unequivocal evidence of this happening. Our best guess is that it's tied to terminator passages at sunrise and sunset, electrostatic charging of the surfaces. So our suggestions are some direct observations of the terminal crossing. If you're awake during the terminal crossing, try and look around for dust. It's not going to be very optically thick, so this is not going to be an easy measurement to make. There's also some evidence that as shadow boundaries change, and even if you're in a lit area, but you're near a boulder and the shadows changes, maybe there's dust levitation in those areas too. Again, that might be a difficult observation, but it might be worthwhile. And of course, any equipment that you're bringing yourself, your own rover, your own hopper and lander, monitor those to see if they acquire or lose dust. Micrometeorite impact flux. Again, this is something that's important for the engineers for their boundary conditions. From a scientific point of view, we think we understand the general micrometeorite flux with a good degree of confidence, but there's always small-scale perturbations that would be interesting to understand that come and go over the 40 years since we've been there. So high-resolution images of surfaces that were pristine 40 years ago and not shielded by other nearby surfaces. So you saw some of the surfaces, like those vertical fins, they're self-shielding in some way. There are other ones, maybe like the lunar rovers, that are not shielded by any other pieces of equipment, and those would give you the micrometeorite flux. Geotechnical properties, we've done a few experiments about geotechnical properties, but we also can infer the geotechnical properties of the regolith from other things like tire tracks, boulder trails, footprints, things like that. So this is how cohesive the soil is, what its load strength is, things like that. And these are not things that we can reproduce on the Earth, and that's an important point. The soils do not behave the same on the Earth as they do on the Moon. Once we bring them back to the Earth, we change them, the water adheres to them, and we can't reproduce every property of lunar regolith with our simulants. Do the best we can, but not every property is reproducible. So these are things that you can only do on the Moon in situ. So, of course, your own ejecta plumes and the interaction with the regolith are important for multiple reasons. This is just one of them. Studying your real interactions with the surface in real time. This is more than just sort of taking a picture. There are other things you can do. You can do scuffs, you can go forwards and backwards, things like that. So this would be an investigation. And then a sort of fun little thing you might want to do is push the biggest possible rock you can over the edge of a crater and observe the descent. This is a little bit challenging. Here you can see a boulder coming down the surface. This is downhill this way and sort of rolling in here. You can see the boulder tracks. There's some suggestion that the regolith right at the edges of craters is fluffy and less cohesive, and it may take less force than you think to push a boulder off of it or to get it rolling. And then the properties of the soil as the boulder interacts. It'll be a little challenging to simultaneously push and observe, but maybe someone more clever than I can come up with how to do that. Okay, so to conclude, we think there are opportunities for new teams to make useful and relevant scientific measurements without carrying any particularly special hardware. Of course, there's more opportunities for science by carrying dedicated science payloads. That is something that is left for someone else to decide, but when we were at the Google Lunar Expo Summit last week talking about this document, there was a strong desire from that community to understand what kind of payloads might be interesting and useful for the science community. And so one of the things we talked about was a participating scientist program. There may be something like a salmon call. Maybe there's a league special action team. If you guys have ideas on how to accomplish that, we'd like to hear them, because there is a desire for this from these commercial communities to say, what can we do that's value added for you? How do we know? How do we know what spectrometer to bring? How do we know what package to bring? So that's something that's of interest. Thanks.
Okay, now for something a little bit different. Do we pull up the first slide? Looks like it's loading. There we are. Okay, well, I'm going to talk to you about something a little bit different. What I want to talk to you about is the opportunity to fly payloads on Google Lunar Express missions. This is a really interesting opportunity. For those of you that don't, probably everyone knows about Google Lunar X Prize, but I should tell the story. The guys at Google, the guys at the top of Google really like space. And after the Suborbital X Prize wanted to get involved in one of Peter Diamandis' X Prize adventures and commissioned the Google Lunar X Prize for $30 million for the first robotic mission to make it to the moon, and there are a bunch of rules. About 24 teams are racing. Their biggest problems are finding startup capital in most cases, and cash flowing their way into a real project as opposed to just dreams of a project. But this is a very important incentive. It's time limited, and some of the teams, in particular a couple, very much like the Suborbital X Prize, are actually well monetized. I'll say something about that later. So there's a possibility to fly hosted payloads on missions that fly. And those hosted payloads could be appropriate for doing lunar geochemistry, geophysics, studying the lunar atmosphere, to do in situ resource utilization, tech demos, EPO payloads, and applications demos like doing lunar astronomy. Basically as wide a field as you can think of. And it's very simple. From the standpoint of the entrepreneurs doing these missions, they're not going to peer review your payload. You may get peer reviewed in order to get money, for example, through Salmon. But from the standpoint of the Google Lunar X Prize folks, do you fit on the bird? Are you going to be safe to my vehicle? And will your check bounce? That's the only three things they care about. So it's pretty simple, isn't it? However you come up with your funding, whether you come through a peer review process like Salmon, or whether instead you find your university foundation, for example, wants to have a payload on the moon and raise it otherwise, the potential is tremendous. In fact, you can even coordinate payloads among multiple landers and build yourself for a single type investigation, whether you're into seismic or you're into something geochemical, or you want to do something with electrostatics, dust transport, whatever the investigation may be, even something as straightforward as a passive laser retroreflector. You can set up your own equivalent of ILN by flying on Javelin. By the way, many of the Google Lunar X Prize teams have the ambition of being in the lunar transportation business. That is, Google Lunar X Prize may be their first mission. They'd like to win that flag and win that check, but they'd like to fly missions again and again. So what does this do? What is the opportunity here? Well, first of all, as you know, the number of opportunities for lunar missions at NASA went through a peak about 3 or 4 years ago, and there's less of them now. And so, and there's also less money. The agency sees very tough pressures externally from the federal budget environment, and there are tough pressures internally to do things like build the Space Launch System to cover overruns, etc. And so pressure from both directions. So flying hosted payloads on missions like Google Lunar X Prize is pretty attractive, because rather than having to come up with $300 or $400 million to fly a Discovery class mission to the moon, the agency can have a slice of such and enable 1 or 2 experiments to fly for a much lower price. So it's the advantage of rideshare. We share the ride, we share the cost. It's also a relatively quick return. Google Lunar X Prize is going to expire in 2014. You'd be hard pressed to write a proposal today and start a project from scratch and get there, I think, by 2016. So 2014 looks pretty close. And there are international opportunities as well, because again, if your check's not going to bounce, if you're not going to hurt my vehicle, and you fit, we're going to fly you. And that means we're going to fly you if your payload comes through another country. So if you have a collaborator in another country that you want to work with a very small number of exceptions. North Korea is probably not the coolest place to get your collaborator, or Iran, or perhaps China. But out of 194 nations on Earth, you got lots of choices, and you can come in through that route as well. So I think this is a pretty rich area for the lunar community to mine, particularly given the current circumstances. You may know that I'm involved in one of those Google Lunar X Prize teams. It's called Moon Express, And Moon Express is specifically in the business of becoming a lunar trucking company, a FedEx that takes payloads to the moon on a regular basis. And we want to win the Google Lunar X Prize, but the business plan is much more expansive than that. That's the icing, not the cake. We're in the very fortunate position of being well monetized. Our two founders, Bob Richards and Naveen Jain, hooked up with Barney Pell, who used to be here at Ames. And some of you may know Bob Richards. He's been involved in Google Lunar X Prize and many other space commercialization ventures. He helped start the International Space University. He also helped start Singularity. Naveen Jain was at the start of Microsoft. And so you can imagine that there are quite a number of billions in his bank account. And Barney Pell, who was a NASA guy working on software after he did his PhD at Stanford, worked on Deep Space One and then left the agency and worked in Silicon Valley as an entrepreneur and got involved in the start of Bing and did very, very well. Bada bing. And so Naveen and Barney together can cover this mission many more if they wanted to. Now, they're not in the business of giving their money away. They're looking for a way to make more money. And they think lunar transportation is a good market. There are a lot of nations on Earth, as I was just describing. Most of them don't have the GDP to easily afford full lunar missions, but many of them have the ability to fly individual payloads on a rideshare basis. And that's the early market. So we're looking to be the first private lunar landing, but even if we're not first, we're looking to do it again and again and again. We're participating in Google Lunar X Prize and looking forward to flying in late 2013 or in 2014. We're pretty far along. We don't have to worry so much as others about how we monetize the project. We have a Space Act agreement with NASA that's taken advantage of the common spacecraft bus that LADI is using so that we leverage on that technology. We've taken over the hover test vehicle that some of you may have seen years ago. It's flying here at Ames. We're flying it now. We're doing a variety of other payload and spacecraft development projects to move towards development and actual CDR for this mission. We've been involved in these ILDD contracts, and when NASA ranked the proposals, we came out first both rounds. So we not only made it across the finish line, we made it across the finish line with flying colors, and we're very proud of that. And we're going great guns right now to finish up our second round on that. So this is one example. This is a shameless plug for how you can get aboard missions like this. Come and see us at Moon Express. Come and see our competitors. Let's make sure that lunar science goes forward even in a constrained budget. And rideshare, Google Lunar X Prize is one way to accomplish that. Thank you.
So just a couple of closing comments. We can bring up the lights. This has been really a significant effort over the last 8 or 9 months with a lot of great experts across the most of the 10 NASA field centers within the agency, as well as some very disciplined experts that have been helping that as well. Margaret Rice and Jeff as well, that have been great contributors to this. I do want to introduce John Guidi from NASA headquarters, Deputy Director for the Integration Office within Exploration System. He is the sponsor and owner of this task, and so we sure appreciate the support and tasking that he's given for us on that. This is still a living document. We're still taking input. It's going into a final form, but we, as I mentioned, we continue to evolve this, and there's roughly 15 copies if you would like one out on that. The X Prize Foundation is assessing it. We did a very detailed briefing last week here in Silicon Valley to the 28 teams, and we're waiting for feedback from them, and then we'll be scheduling up in the next few weeks a press conference out of Washington that does more formally introduce this whole package. So we appreciate Greg and Yvonne for allowing us to come and share some of this as a part of the Lunar Science Forum. And with that, we'll open it up to questions to the panel.
Yes, I just have a broad question. For the U.S. government, keep out no-fly zones have always been the purview of the military. Has there been any chatter, influence, or comment from this sector?
I'm sorry, I didn't quite get the question, if you could.
Say it slower. For the U.S. government, which is those sites that you were referring to,
Yeah.
keep out and no-fly zones have always been the purview of the U.S. military. So I'm asking you, has there been any chatter, influence, or comment from this sector?
Not from the military. These were just basic terms we use to help delineate within these recommendations boundary conditions. So no, there's been no involvement with the military.
No, I'm not asking if there's involvement. I'm asking if they're paying attention. Do you know?
So let's see. We have done some outreach to notify various levels of government agencies, to include FAA, the State Department, OMB, OSTP, White House, but I don't know necessarily that we've talked to DOD. John's shaking his head no. Margaret?
Well, just since this is part of Outer Space Treaty activities, the Outer Space Treaty says no military. So assuming that we're adhering to it since we are a signatory, then the military might be interested in seeing what we're doing, but they wouldn't have any reason to interact or comment or...
Other questions?
I can't remember, it was early on in the talks talking about what areas were off limits to driving around. I think 11 and 17 were completely blocked off, and 14, 15, 16, and 12 were open. I would suggest putting a keep out zone around 2 sites at Apollo 15 for remote sensing ground truth. In particular, one of the where the soil sample was taken along where the Highland Maury contact boundary is, and another one out in the Maury boundary. It wouldn't have to be a really super strict keep out. If you had a very small rover that went in there and did some sampling or geochemistry, that would be totally awesome. But some high energy vehicle or human beings, which are very high energy, but we don't have to worry about that right now. Because what it'll do is churn the soil up, and this would be something like a 50 meters area, so that a pixel that was looking on that from, say, an imaging spectrometer or something along those lines, would have a more or less pristine look at that, so you could compare the spectroscopy to the geochemistry. Kind of a minor point, but worth considering maybe.
Terrific, yeah.
I think we totally forgot about the ground truth sites. So thank you for bringing that up, and we should incorporate those.
Other thoughts, comments?
In aviation today, there are plenty of examples of areas where you have restricted airspace that are not military in nature, such as flying over national parks, and that might be a more appropriate model here.
Well, also airports, the FAA regulates who can fly over an airport.
Yeah, again, let me stress that these are technical recommendations. These should not be construed as hard and fast, thou shalt, cannot. We cannot enforce people from going to the sites. NASA doesn't have any claim to the property. We own the artifacts, but these are notional boundaries that we think have technical relevance in preserving and protecting these, both scientifically and historically. So I want to make sure that's clear that these are recommendations, but based on technical fact and analysis in constructing these various boundary conditions.
I have a
Fred?
quick one.
I'm sorry.
You recommended a 1 meter standoff distance as kind of a ground rule, but also there was a desire to see surfaces of witness plates.
Yes.
And it seems like you'd want to get in really close to have a microscopic examination.
Right,
So that,
exactly. And actually, we've done some analysis on some of the basic imaging systems that some of the teams are considering. And based upon the distances that we think they can get within the 1 meter buffer, and the imaging technology that exists today, that resolutions down to 0.1 centimeters is very doable within these systems that can give us some insight, for example, into the micrometeorite impact flux and cratering within reflective surfaces, et cetera. So yeah, we just don't want contact. The 1 meter was a subjective number, but to minimize the chance of contact, but again, allow close enough inspection to the flight hardware. Yeah, that's a great comment, Wendell. Yeah.
It occurs to me that this is a rather unique opportunity. These guidelines, of course, are voluntary. You don't have the right to enforce them. But they're also, I think, extremely important as a precedent, because if you're looking at a commercial activity, for example, what is the operational boundary that, you might make some claim to, and if you're ice mining or doing any some other sort of commercial related activity. And so part of my question to you, in the formulation of these guidelines, has there been any international discussion relative to a courtesy in this protocol? These are guidelines, but for anybody, the Russians, for example, they would have a similar stake in preserving and protecting the Lunar rovers, and were they to do something or revisit them, the courtesy that's extended, it's kind of the law of the sea. You start to observe these things, and over time that becomes more of a legal precedent. Yeah. If we look at a growing lunar community, I wonder if this has been kind of processed or kicked up to that level, so that there's building expectations that have the ability to share and to respect and to look at this. Like, what if you don't own it? You can, in theory, I can do anything I want to do except come and steal your hardware.
Yeah. So great comment. Two thoughts in response to that. One is we have done notifications of the package to the international partners through the forums out at NASA headquarters. And secondly, as I mentioned last week, these individual commercial companies, whether it's Allen or Fred or whoever, if they're the first to land, they become very historic in their own right by being the first privatized commercial group to set down on another planetary surface other than a government agency. So, similar to the way we're thinking about protecting or assessing our hardware, it applies to them as well as Russian hardware. These certainly could be used as templates to other groups in the protection and assessment of these, and that is certainly open to them for consideration.
If I could just remark, I think from the standpoint of the entrepreneurs, as many of them as not are probably very happy for others to come right up to their hardware, take some, and we'll just charge you for it.
Other questions? Fred?
Isn't there an international treaty that protects active scientific experiments from being tampered with by another party? Or am I misinformed on that?
I don't know. That it has never come up within the legal representatives that we have at NASA headquarters. It's something we can go check, Fred.
Okay, it's something that I heard in a discussion earlier
our
today.
Our legal experts have advised us on.
That's something I heard in a discussion earlier today. And my other comment for Alan on your presentation is that the Google Lunar X Prize does not end in 2014. The prize is set to write down in the first prize amount on December 31st of 2015. And at that point, it becomes a $15 million prize, and Google has the option to terminate or continue it.
Okay, well, thanks for the clarification.
Other thoughts, questions?
Brian O'Brien, you've got constraints on the descent stage. Do you have any constraints upon the activities that might, so to speak, cross the no-go zone, for example, with active grenades to do some testing, things like that, in the vicinity of the the rover? In other words, intrusion or chemicals or whatever that would cross the barrier.
Yeah, so great question, Brian. We've tried to deal with that to some level by dealing with not parking or having intermission life of these systems within the boundary so that we don't have those type of events that could contaminate or damage the site. But I go back to the original premise is that these are based upon the architectures as we understand them today, and right now none of them are planning to lob grenades, and there's still grenades up there, I guess, right, Brian? And within one of the ALSEP packages. But none of them, I don't think Fred and others are planning to do any grenade launching at this point.
I'd like to add a thought. There are some aspects of the plume effects that we still don't understand, and we have not written an overly conservative set of guidelines because we haven't drawn tremendously broad boundaries around the areas of uncertainty. In particular, when you launch off the regolith, there is a shock effect from the ignition of the engine, which causes a splash of soil, and it's significantly different than descending, in which you slowly build up a shock wave over the surface. We really don't understand the physics of that very much, but we haven't tried to create tremendous boundaries. But we would like to get data from the lunar environment to find out what happens during a launch event.
I guess the point of the question is, I'll shout. The point of the question is you'll have to face up to the precautionary principle at some stage, because there'll be worthwhile experiments proposed for the simple reason you don't know what the answer is going to be. And the answer may involve intruding
Okay. I understand your question now, Brian. So we've dealt with that within the authority framework of the section and have said these are basic guidelines and principles, but we can handle case-by-case basis in working and coordinating between the U.S. government and the commercial landers in this case for any of those type of activities that might fall outside the framework of the basic document.
Yeah, I guess I still haven't made the point, sorry. An exclusion zone is a binary system. You haven't specified what it is you're worried about.
Oh.
And hence, it's going to be hard to apply the precautionary principle to innovative experiments, which might...
Okay. No, we tried to do that, Brian. Maybe it's clear when you read the document, but the risks were associated within these boundaries, or is the casting of dust, where we're concerned about the collision risk, we're concerned about contaminating the site, whether that's toxic material or dust or other things. So we've tried to think about the risk perspective and then suggest mitigation approaches relative to the boundaries. There might be things that fall outside of that we haven't thought of. There probably are, but that is the basic framework from which we had established these boundaries.
And Rob, since it's a living document, if somebody came up with a proposed experiment, then you would address that at the time, right?
Right. So that was the point, that through the coordination with the government, we can decide how best to handle that.
Question here. Have you thought about the next phase where you might want to bring something back, and do you see that as a potential contest that the X Prize might?
I can't answer the contest since this wasn't even our contest. We're just responding back to concerns out of Google and Lunar X Prize. We recognize the sample return is something of high interest, but again, it fell outside the framework of the basic architectures. When the technology or groups are interested in doing those type of activities, then we'll add that within the overarching document.
Okay, what if you were going to bring something back for analysis, what do you think that might be from these sites and landing areas?
When I think that might be?
No, what? What would you want to bring back for analysis?
Well, I'll ask Mike to respond to that from an engineering standpoint, and then Barbara can respond to that maybe
A
from
rock.
a rock.
But, I mean, the Apollo equipment or any of the 10,000 things that are hardware.
Yeah, I mean, I can't tell you specifically. I mean, the options are boundless. Depends on how much they can bring back. I'd say as much as they can. You know, if a given mission is planned, then at that time we'll look more specifically at what's available, what's easily detachable or cuttable, and go from there. You know, our guidelines were very broad and looking at all the different things you could look at. I can't tell you what our priority would be as far as bringing back.
I would think that a couple of examples of
I've
things.
been kidding Mike about the golf ball all week, that, you know, if it hadn't exploded and vaporized and, you know, that would be really cool, you know, to see Max fly 3-dot, you know, on that thing. That would be really neat. Yeah, I like the golf ball. Well, that's true. That'd be a good question mark.
Well, I think that from a scientific perspective, a couple of the
Wendell?
types, excuse me,
Oh, I'm sorry.
yeah. Can I try to answer? May I?
Oh, sure.
Good. I think that a couple of things that would be of interest that are easy to return are exterior mylar on spacecraft surfaces, so that one can study not only space aging effects, but also cosmic ray implantation, and very much like the solar wind collectors, sort of a free solar wind collector / micrometeorite impacts on those surfaces. And the Apollo crews all left behind biological materials on the surface. I'll leave it to your imagination, but things were bagged up and left behind, food, trash, other things. And I would think that there's going to be an interest in looking to see what survived that long exposure.
I'd like to add a little bit to it also.
Yeah, that's amazing.
Let me add a couple more thoughts on what I would like to see brought back. I don't know if NASA would ever agree to this, if the decision makers would agree to it, but I'd like to see the lens of the LRV camera brought back because it was degraded during ascent and we could see the degradation of the video, and I'd like to characterize the roughening of the lens because that would allow us to calibrate our models. Another thing is pieces of mylar that were blown off during launch, during ascent, are scattered over kilometers, and you can get those without going inside of any of these boundaries.
Fred?
Okay, you mentioned earlier there was potential for live decision on whether or not we could enter into an area and look for something in particular. Will there be some sort of, would this be on the participating scientist program where we would have someone during our mission operations who would be present and could make a decision from your perspective, from the NASA perspective, as to what made sense and whether we would be allowed to go into the site, to make closer inspections of hardware and that kind of thing?
I don't think we've addressed that to the real-time aspect at this point. What we addressed in the document was pre-flight coordination for areas of interest, but we really didn't address very deeply the real-time execution.
Okay. And then, Alan, if you're going to bring back biologicals, don't we need a baseline sample from the same time period from the same astronaut to compare it to? You don't have to answer that.
Let's see, over here, Clive?
Just to change tack a little bit, if there is going to be an amendment to the salmon call and participating scientist program, we've gotten the data, we've sent it off to headquarters to try and get that, but a question for Alan and other XPRIZE teams here. Will there be a list of available mass, power, datacom to the science community so that any of these salmon, if there is an amendment to the salmon call, we can get instruments available, we can get, we have a pricing or a cost that we could also put in there to get funding for, so we can take advantage of this very unique opportunity?
Yeah, I can't speak for other teams, and I know that there's no global effort across the Google Lunar XPRIZE to organize anything like that, but I can tell you that Moon Express is in the process of putting together a payload user's guide for just that purpose.
George Reed wrote a couple of papers from Argonne National Laboratory on the mass transport of mercury through the vertical column based on thermal-driven mass transport. It would be interesting to take a look at the soil underneath something that was creating an artificial shadow and see how that varied with a region that wasn't shadowed. This would be something that had shadowed something only for 40 years rather than a shadow that existed previously under boulders.
Yeah, so NASA can't enforce the exclusion zones, but are there any proposals for industry self-regulation where maybe the XPRIZE Foundation would say you're disqualified if you break these zones or something like that?
Yeah, I mean, that's a great question for XPRIZE. We can't speak for them. They're assessing the document, so I would hate to conjecture what they see as how this plays into their rules and judging panel.
There is no rule that gives them the authority to disqualify us for that right now, and we've already signed the MTA. If they were to try to insert some new rule to that effect, it would never pass because all of the teams now have veto authority over any change such as that. Unless, we'll qualify with that with one option. If it were a law, they can change the contract to be in compliance with law. So if a law came into effect which restricted a team from accessing a site based on permission from NASA or some other governmental body, they would have the authority to change the contract. Otherwise, it won't happen.
I think that I heard right that the idea is to approach and up to 1 meter away from items. Is that right?
Correct.
One of the unexpected things that came out of the dust detectors on Apollo was the amount of dust, collateral dust, that the astronauts splashed on the experiments and the hardware. And that's all right, you can photograph some of it, but some of the heating effects and some of the experimental effects are probably from the finer dust that you can't photograph or see, and of course that'll travel further than the nominal heavier stuff, even for a slow-moving rover. And I wonder what physics has gone into this construction of the 1 meter approach distance?
So good question. I didn't show all the recommendations in here, Brian, but what we actually went and looked at angular wheel speeds and the casting of dust or throwing of dust as a function of wheel velocity to help minimize as a function of distance what wheel speeds are acceptable at a functional distance to try to mitigate any casting or throwing of dust that may artificially be deposited on the flight hardware. We'll take maybe 1 or 2 more questions and then turn it back to Greg. Well, thank you so much for letting us come and share with you this analysis and the package. Again, there's